All right, hello everybody. Welcome to EEE146 Power Electronics, where we're going to continue on Chapter 3, Half-Wave Rectifiers. So last week we talked about the basic half-wave rectifier with all the different types of loads. This week I want to talk about the additional features and components we could put onto an existing half-wave rectifier to improve the performance. One of the first things you can always do is add a freewheeling diode, which is this extra diode. Now, why do we have that? If you remember from last time, one of the big complications for having an inductor, and what did it cause? Remember, it forces a current when the AC source is on its negative cycle. And an inductor does not want to stop. It wants to keep on going. So you're going to have negative voltage on the output for the current to flow, which isn't really ideal. We want to have a higher voltage, not a negative voltage. But the inductor forces it. Okay. This also causes complications for the AC source, because when the AC source is negative, it doesn't want to be pushing a positive current. It's kind of really funky for the AC source, and it could cause some problems. So how could we compensate the extra current built up into the inductor? Well, one of the easiest ways to do it is let it bleed out. Have a convenient path for the current to flow have a convenient point for the current to flow out of the inductor that's not the source, kind of like a bypass channel or alternate path. Okay, so let's have a bypass path for the current to dissipate into the load resistor. That way the AC source isn't affected. And that's what this diode does. Once this diode is here, when the source voltage goes negative, the current's going to stop flowing through D1, but the inductor current will still want to flow, I0, but we have this D2 right here as a convenient path for the current to flow right here, right? So this kind of helps out. And this is called a freewheeling diode right here, okay? So end of the day, literally, it's there to help the inductor bleed its own energy out to the load resistor, not back to the source, okay? In almost every modern converter is going to have some type of bleed out, some type of freewheeling diode. Some people call it bypass diode or a bleed out diode, or some of this form. But the ultimate goal is to let the inductor current flow out. Okay. Now, what happens whenever the source voltage is on its positive half of the cycle? Okay, so let's assume we're in a positive half of the source voltage waveform. So current's going to flow out the positive terminal. It's going to go through diode 1 because it's forward biased. And go through the load and back to the source. Current will flow in a clockwise direction. Okay. And what ends up happening here is this top voltage up here is high voltage and this bottom voltage is low. So for D2, current's going to actually want to go down the page. Because if we have like 10 volts here and 0 volts here, current's going to flow down. But we're flowing against the diode, so it's going to be reverse biased. Okay, so kind of answer pretty much what I'm saying is observe the circuit above. What's the main diode D1 doing? Forward bias is conducting because source voltage here is greater than low voltage on the other side. What is the freewheeling diode D2 doing? It's reverse bias because the positive terminal up here is a high voltage of Vs, while the negative terminal is 0 volts. Okay, so it's reverse bias, current's never going to flow. And of course, I said draw the path, current in blue. Okay, so this is business like usual. Nothing's changed so far. But now on a negative voltage source, so let's see what happens. So let's assume that we're on the negative half of the source voltage waveform right here. So current's going to want to flow out on the negative terminal, and current's going to want to flow into the positive terminal because they're negative, but D1 is reverse biased, right? So observing the circuit above, what is the main diode D1 doing? Is reverse biased because this Vs right here is negative, and we have a positive voltage here. Current's going to want to go to the left of the page, and the diode stops it. Okay. Now, what's a freewheeling diode D2 doing? Remember, we had current flowing through an inductor previously. Just because we turn off the source doesn't mean the inductor stopped. It's going to keep on going, But now the inductor turns out to be the new voltage source in the circuit. So an inductor is acting like a voltage source. So you can even put a positive and negative V right here. This bottom part is going to be the highest point in the voltage right here. Okay. And it's going to want to flow out down this path. It cannot flow to the source because this is a positive voltage. So it's not going to want to do that. Instead, it's going to flow down through D2 to quote right here, where this is now the 0 volts of the circuit. And it's going to flow back to the resistor and inductor. So it's going to kind of flow in this fashion through diode D2. Okay, so D2 is forward bias, inductor voltage applies forward voltage across a freewheeling diode, and then we're just going to conduct. Okay, at this point, the source voltage doesn't even do anything because there's no way for the current to flow back into the circuit, so this module will be gone, right? Even if this is like 500 volts or something, it doesn't matter because this top terminal can never get down to this point right here, complete a circuit. So it's like a voltage source that's just half connected to the circuit, it doesn't do anything, okay? So one major loop where the inductor just bleeds its own energy out to the resistor, and eventually this becomes 0 volts, right? After an inductor bleeds all its energy out, then the circuit's inert and nothing's happening, okay? So you gotta remember the whole point of the freewheeling diode is just a convenient path for the current to flow. Now, since we're using an inductor that's charging and discharging in the circuit, there is a startup transient. A lot of times an inductor in a load doesn't fully dissipate. It might dissipate to half, 50%, and then the cycle starts again. It might charge from 50% to 90%, then 50% to 90%. It's not always 0 to 100%. It really depends on the load and your voltage source. Okay, so whenever it's not that full charge and discharge mode, it's somewhere in the middle, you're going to have to start the circuit at 0 volts. So literally the circuit's been dead for like 3 days. You flip the switch on. The first couple of cycles, so this is like one cycle of the AC waveform, a second cycle, the third cycle, right? It takes time to actually charge up the inductor. So we'll start from 0% charge and maybe 50, 60, 70%, go down to 30%, go down to 8%, go down to 50%, go down to 90, 60, 100, 60, 160, something like this, right? So it's just, you have to start charging up the inductor from 0, and then it'll eventually stop charging and reach a steady state where the inductor energy is going to perfectly balance with the source energy, and now it's going up and down, is bleeding out and absorbing energy, bleeding out, absorbing energy at a constant rate, right? So why is this? Why is there a transient state in an inductor? When the circuit turns on, we need to charge an inductor from a dead state. Again, once we're in a steady state here where nothing changes, the inductor energy is not 0. It's gonna be maybe 50%. So it's gonna, let's say it goes to from, I think I said 90 to 60. So it's a 30% swing for every cycle. Okay. So what happens after the transient state, about right here, the inductor is fully charged and ready to cycle energy storage at a constant rate. Okay. So any type of circuit with an inductor capacitor with an AC source, you're going to have this kind of transient state for everything to turn on, and then you reach a steady state, and then we're going to be operating like normal. Okay. So let's look at the output of the freewheeling diode and how this output of the circuit behaves. So look at output voltage and output current, because that's what matters the most, because we're sending this to the load. So notice we have a positive cycle of the output voltage right here, V0, V out, sorry. While V out is positive, look at the current, it starts increasing. So this is a normal current right here. It increases because an inductor is getting charged up, it's letting more current through. When an inductor gets charged up, more current flows through. More current flows through means the resistor gets more power. We're powering the load. So when we power the load a little bit here, we're going to build up, we're going to power the load a lot. Okay. Now, once we get to about 180 degrees, the output voltage goes away. But the current is still going to be there because of an inductor. Now, it will start bleeding its energy out. So once an inductor starts bleeding energy out, the current can get less and less and less, right? An inductor fully charged can push out more current than an inductor at 50% charge. And there's a slow decay like so. And eventually at 360 degrees, it repeats itself over and over. So that's how you get your up and down waves of blue is charging, green is discharging. Blue is charging, green is discharging. Okay. When is the main diode D1 conducting within this charge and discharge cycle? Remember, this is when the voltage source is on. So whenever we have this red waveform where the source is active, the halfway rectifier is acting like normal, you have a positive current that builds up. Once the voltage is gone, between 180 and 360 degrees, this is when the freewheeling diode D2 is conducting. So notice you have this line right here. This is where diode D2 conducts. When the source voltage is absent, the inductor is a temporary source, and then we still power on circuit, and then we'll do it over and over and over again. So think of like it ping pongs between D1 to D2, D1 to D2, and just back and forth and back and forth. Okay. Now, with that, we have to do a lot of harmonic analysis because that waveform we showed you is not a nice waveform, right? Let's go back and look at it. You have this nice little kind of hump up here. You got this more straight line over here, right? This is not nice waveforms to deal with. This is not a purely sinusoidal waveform. It's also not at the zero axis. So this is a very hard waveform to mathematically show with just a single sine or cosine. It's actually impossible. So that's the one downside of freewheeling diode and an inductor. It starts creating some wonky waveforms. But in power electronics, we have to be ready for wonky waveforms. That's just the nature of the game. We're playing around with energy storage. We're doing a lot of random switching around. So we're not going to have easy, nice waveforms. This is why you learn harmonic analysis, because this is a way to quantify those weird waveforms mathematically to do circuit analysis. So let's repeat ourselves. Here is a voltage. Let's say output voltage. Okay, now let's go back up. Look what output voltage is. In this case, it's 0. It's a normal AC waveform from 0 to 180 degrees, and it's flat 0 from 180 to 360, and it repeats itself. Now, if you put a conditional statement, you can make this as a pure sine wave. But if I don't want to use a conditional statement, we need harmonic analysis to show half an AC waveform, flat 0, half an AC waveform, flat 0. And we can do that. It is possible. So your output voltage will always have 3 major components with harmonic analysis. You'll have a DC offset, which is you can calculate it as Vm over pi, right? And I like to say this is n equals 0, means it's this no harmonic, it's just a DC component. Then you got your fundamental harmonic, Vm over 2 sine omega t. This is just your 60 hertz signal, your basic AC waveform. If you go up here, you can imagine that this waveform right here is your n equals 1. Now, if it's a purely sine wave, you're going to have a negative cycle right here. We have to subtract the negative cycle away, and that's how we're going to use harmonics. Notice we have this negative sign, so we're going to subtract a bunch of higher order harmonics to make and force that wave flat on between 180 and 360. And if we get very creative with our harmonic selection, we can absolutely do that. Okay, so here you're going to subtract all your harmonics from n equals 2, 4, 6, 8, 10, 12, even order harmonics till it doesn't matter anymore, right? Mathematically, you go to infinity, but in real engineering, we're going to keep doing this iteration until the waveform the answer doesn't change, and then we could just stop, otherwise we're wasting our time, okay? And for this particular halfway rectifier, it's going to be each harmonic can be calculated as 2 times the maximum source voltage. For Vm is the maximum of the source. So if I go all the way back up here, sorry, I know I'm going up a lot. It's this right here, okay? That way you're not getting lost. Okay, 2 Vmax divided by n squared minus 1, where n is your harmonic order, times pi times cosine nw1t. So you have a sine and a cosine put together, so you can add sines and cosines together. It's not that hard, right? All you have to do is just find this magnitude. So at the end of the day, remember, harmonics is just a number. This will be a number, Vm over pi for 0. VM over 2 for n equals 1. That's just a number. This might look scary, but at the end of the day, a summation just means add individual ones. So we could do a minus this for 2. You just plug in 2 here. This is a number crunch. And then you'll minus a 4 here. You number crunch this. You minus a 6 here. You number crunch this. Okay. So a lot of times all this mathematics, it just really devolves down to just a number that we care about in engineering. Okay. So kind of said right here, but I'll repeat it. DC, here we have 3 components of the output voltage of this Fourier series: a DC component, an AC component where it's part of the AC source and passed through the main diode, and this typically n equals 1 is 60 hertz for America. And then harmonic, higher order harmonics to shape the half wave rectifier output, right? Since we remember we cut off the negative cycle. Now, remember the whole point of this is now if we could quantify that voltage in harmonic and in harmonic terms, we could then do circuit analysis with harmonics. Just remember, as we do circuit analysis, the inductor XL changes because the frequency changes per harmonic. N equals 1 is 60 hertz, N equals 2 is 120 hertz, N equals 4 is 240 hertz, and so on and so on. Okay? Now, when we talk about harmonics, right? Harmonics is a bad thing, so we want to mitigate them as much as possible. So all the subtract those n equals 2, 4, 6. If we design a circuit right, those numbers should go down and not be that big of an issue. Okay. Now for the voltage, we can't really do much, but for the current, we can reduce the harmonics. The more flat and DC-like the output waveform of the current is, the less their harmonics are going to be. Okay, remember, more harmonics equals more messed up waveform, further away from the ideal waveform. Ideally, we want the output to be flat. So if we make the inductor bigger, it will resist a change in current more. So instead of having big wavy waveforms, a giant inductor will make it very flat. It will have a little waveform, a little up and down, but it's going to be predominantly flat. If we make it big enough, we could pretty much smooth out the output to a near DC level, right? To where your output voltage, you might have this output voltage here, 0 to 180 degrees, then it's flat, and then 360 or 0 to 180 degrees again is flat. But with a giant inductor, we can make the current completely flat, or it's going to be so flat, you're not even going to be able to see it. There'll be a little wiggle. There'll always be a little wiggle, but from a naked eye, you're not going to see it. From a circuit analysis standpoint, it's going to be less than 1% of a ripple. It's not going to really be a big deal. You could ignore it. Okay. And the way we do this is let's just look at the current. Remember, current is V out over R, which is V out is just VM over R, pi. That's just from here, right? Times R. So this is your output current. If we make the inductor so much bigger than a resistor, this output current will be only based on this root. Sorry. If we make this inductor much bigger than this resistor, so this L over R ratio is approaching infinity, the inductor current will pretty much be DC, and then this will be a DC circuit analysis where you just use Ohm's law now. You don't have to do this harmonic analysis. And that's the key component. Now, what's this infinity means? In real life, if you can get a 10-to-1 ratio, that's probably enough to say it's infinity. Meaning if my inductor is 10 times bigger than my resistor, and this is in Henry's, by the way, so that's a really big inductor. If I got 10 ohms, I need a 100 Henry inductor. That's gigantic, okay? But it is possible. That's going to be infinity, equivalent in real circuit analysis or practical circuit analysis, okay? So once we get that 10-to-1 ratio, this is what output current is going to look like. It's going to be pretty much flat. And notice from the diode D1, this is the main diode. It's going to be flat, and it's going to be 0. It's going to be flat. It's going to be 0. Look at the diode D2. This is a freewheeling diode. When D1 is not activating, D2 is, and they're both flat as well. Add them together, you can get this flat waveform up here. Okay? So, low current harmonics, just make a big inductor. You don't have to worry about it. That's the goal. Voltage, you still have to deal with it. You can't get away from that yet. Okay. So let's do some math. Let's do some circuit analysis to show you how to quantify this. Again, harmonic analysis, it's a lot of work, but it's just a method. We just follow their steps, and then we could get it done. It's going to be a lot of arithmetic, but we can actually get an answer. So here we have a voltage source, AC, a half-wave rectifier, a RO load, and a freewheeling diode added in. Okay. Determine the average load voltage across here, the load current right here, and the power absorbed by the resistor for the circuit below. Okay. VM is 100 volts at 60 hertz. Resistance is 2 ohms. L is 25 millihenries. Okay. So let's use Fourier analysis up to the second order harmonic to see what we get. So we got to always start with 0. So V out right here. So they level V out from this right here, plus minus V out. But remember, it's a whole bus right here. So this point is all the same. This down point right here is all the same. The output voltage is just Vm over pi, which is 100 volts divided by pi. The average voltage is 31.8 volts across this load. What's the current? Because it's DC, the inductor doesn't do anything. Inductor is a short circuited DC component. So it's just Ohm's law. I equals V over R, 31.8 volts divided by 2 ohms is 15.9 amps. That's your average current. So that's for your DC component. Okay. And at the end of the day, for average voltage and load, the DC is all that matters, right? Because the inductor will make the voltage higher at some point, but it's going to make it lower at another point. Sorry, the current. It's going to make the current higher at one point, lower at the other. At the end of the day, they're going to cancel out, right? The average for an AC waveform is always 0. So the DC is only one that really matters for the pure averages. But if we want to find power absorbed, we have to use harmonic analysis because we need to find the power for the AC side as well. Okay. So let's now go to the AC component of your output. We did n equals 0. Let's do n equals 1. That's that 60 hertz signal. Okay. So right here, we have a RL load. We need to convert that to phasors at 60 hertz. So we know Z1, and 1 denotes the first harmonic, equals R plus J N omega 1 L. R is just 2 plus J, that's just the imaginary operator. N equals 1, so we put a 1 right here. Omega is 377 radians per second, and L is 25 millihenries. Okay, you just number crunches, we get 2 plus J, 9.34 ohms. So that's the impedance of the load at 60 hertz. What's the voltage across here? Where V1 is equal to Vm over 2, right? Go back up here. It says it right here, Vm over 2. Okay. So that's just 50 volts. After that, let's do Ohm's law. I equals V over Z, except we got to do phasors. So we have 50 volts. Angle, we'll just say the angle is 0 degrees. I probably should write that, but I got lazy. Divided by 2 plus J, 9.43 ohms. This is AC, 100%. The answer is 5.19 angle negative 78 degrees amps. We probably don't need the angles, but I wrote it there just to say it. The big two numbers is I know V1 is 50 volts. I know I1 is 5.19 amps. Okay. Now we got to do for n equals 2 right here. So repeat the whole process again, except we're going to, everywhere there was a 1, we put a 2. Because the circuit's not changing, so the formulas are all the same. Z2 is equal to R plus J2 omega 1L, right? And you plug everything in, it's going to be 2 plus J2 times 377 times 25 milli, which is 2 plus J, 18.9 ohms. So the only thing that changed between previous one and this one is the inductor doubled in impedance, which makes sense. You went from 60 hertz to 120 hertz, right? Now the voltage, V2, is going to be a little more complicated. Remember from the equation up there, it's going to be 2 Vm divided by n squared minus 1 pi, which is equal to 2 times 100 volts from right there, divided by, now because n equals 2, we get 2 squared minus 1, so this is 3. and then divide by pi as well. You number crunch this in your calculator, you can get 21.2 volts. So let's just do Ohm's law. I2 is equal to V2 over Z2. We got 21.2 volts divided by 2 plus J 18.9 ohms. Our total current is going to be 1.12 amps at an angle negative 84 degrees. All right. So here you got a smaller voltage and a smaller current, which is expected as you get higher order harmonics. These numbers are going to typically get less and less and less. Okay. Now we got I0. We got n equals 0, n equals 1, n equals 2. We could find the total power. Remember, to find the total power, we need to find the RMS of all the currents in the circuit, not just the DC one. This is why we're doing harmonic analysis. To find a total current going into the load, IRMS is always equal to the square root of all our harmonics squared and then added together. So you get I0 squared. You get plus I1 squared plus I2 squared and any more you have. Now, all these values inside here must be RMSs. To get a total RMS, you got to add the sum of squares of the individual RMS quantities. Okay. So DC current is always an RMS quantity to begin with. So you just I0 square that plus I1 divided by square root 2. So why do we divide by square root 2? Because this is AC voltage and AC current. Notice up here, my voltage, I gave you a magnitude. I did not give you an RMS for the source. So you could divide by square root 2 right here. So you could literally say 100 divided by square root 2, go through your whole calculations, and you wouldn't have to put it down here. Okay. But we kept magnitudes everywhere. We didn't touch RMS through harmonic analysis. So our total answer, I1, is another maximum or magnitude of a sine or cosine waveform. We need to take that maximum and divide by square root 2 to get the RMS of the first harmonic. Okay. I just want to reiterate, if you already have RMS quantities to begin with from your voltage source, you don't have to divide by square root 2. But in this course, for this type of problem, we typically don't do that because it gets a little more confusing. So we just take the RMS value at the very end. So I1 divided by square root 2, don't forget to square that, plus I2 divided by square root 2, same logic, square that, square root the whole thing, and then at this point you just number crunch this, 15.9 squared plus 5.19 divided by square root 2 squared plus 1.12 divided by square root 2 squared, square root the whole thing, you get 16.34 amps. Okay. So what's the power that's coming out of the load? That's very easy. P is always I squared R. Remember, inductor does not produce any power at all in watts. It produces VARs, but we're not talking about VARs. We're not talking about Q. We're talking about real active power, P. So P is always going to be I squared times R, which is equal to 16.34 squared, we just got that, times 2 ohms, which that's given to us. We get 534 watts. Okay. So at the end of the day, we answered 2 questions. 3. Load current, 15.9 amps. Load voltage, 31.8 volts. The power absorbed by the resistor from the source, 534 watts. And this is what the real power is. That's the real work being done. Charging the battery, turning the lights on, running the motor. This is what ultimately matters at the end of the day. Okay. So here we're going to take our 15-20 minute break where we're going to do exercise where I want you to continue what I started. I want you to take the n equals 0, 1, and 2, save that. I want you to do another harmonic order. So continue my problem, do this whole setup right here with n equals 4. So you know what to do, you know what to change to make that happen. Okay? So let's do more precise for Fourier series analysis. Give me an update to the current RMS and power absorbed. So this power absorbed right here, this IRMS current, add in an n equals 4, and let's see if that number changes. Let's get a more accurate answer. Okay, so this page, do your harmonic analysis for the 4th order harmonic, and this page, figure out your current RMS, figure out your total power absorbed. We'll come back and check your answers. Okay, so good luck. See you guys in a second for it. Okay, hello. Welcome back to EEE146 Power Electronics. Back from our 15-20 minute exercise on this halfway rectifier where we did the fourth order harmonic to add into our analysis. So let's see how we did it. So n equals 4. So we need the impedance of the load for Z of Z4. This is equal to R plus J4 times omega 1L is equal to 2 ohms plus J4 times 377 radians per second times 25 millihenries. Number of current is 2 plus J3, 37.7 ohms. Okay. V4 is 2 Vm divided by n squared minus 1 times pi. So it's 2 times 100 divided by 4 squared minus 1, which is 13, divided by pi, which is 4.12 volts. And then you do your current. Current is Ohm's law. I4 equals V4 over Z4, 4.24 volts divided by 2 plus J, 37.7 ohms. We get 0.11 amps and angle negative 87 degrees. So this is why as harmonic order gets higher, number one, your impedance gets higher because inductors get bigger. Capacitors do get smaller, right? If you ever see a capacitor. But the big thing is look at your voltage. Because we divide by n squared on the bottom, it gets less and less every time. So the higher order harmonics actually don't do nearly as much as the smaller ones. And note in case, our current is just 0.11 amps. That's not that much. So let's see how much of a difference it makes. So remember, current RMS is always I RMS equals square root of all the each individual harmonics RMS squared. So you have I0 squared plus I1 divided by square root 2 squared plus I2 divided by square root 2 squared plus the new one we just calculated, I4 divided by square root 2 squared. So now we're crunching all this, 15.9 squared plus 5.19 divided by square root 2 squared plus 1.112 divided by square root 2 squared plus 0.11 divided by square root 2 squared. Square root everything is 16.34 amps. That's pretty much the same number we got before because we rounded off all the decimals. The reason why is 0.11 amps is nothing. I mean, like if you calculate all this, this is the biggest contributor right here, 15.9. Then this is another big one. Even n equals 2 to 4, it's a 10 orders of magnitude difference, right? You literally move the decimal place once over. Anytime in engineering where you move a decimal place once, that's a huge factor in terms of the output. It's like going from 100% effectiveness down to 10% effectiveness, right? So anytime you have two numbers where one is 10 times less than the other, it's almost a non-factor. It's less than a 10% difference, if not even smaller than that, right? So at the end of the day, this is literally a rounding error. So power absorbed is going to be the same as before. P equals I squared times R, where it's 16.34 amps squared times 2 ohms is 543 watts. So just wanted to use an exercise to show you how to do the fourth order harmonic. But one thing we get out of this is this harmonic did nothing for our output. So if I'm doing my calculations to get the most accurate number, I will start with 0, 1, absolutely have to do 2. Honestly, the fourth harmonic, I see I didn't change from going from second to fourth too much. By adding in the more work, there is no reason for us to go to n equals 6. Because if 4 didn't do much, 6 is definitely not going to do anything, right? So that's the big process I want to show you is whenever you do a harmonic analysis, go one by one. And you have to at least do 0, 1, and a single harmonic, 0, 1, 2. Then do the higher ones and see if it matters or not, okay? And I'd stop where it doesn't matter. So this right here, fourth, is where I'd stop and say, I think we're good in terms of our calculation for that circuit. Okay, so that's harmonic analysis for you. The other couple of things, or big one I want to talk to you about now is the capacitive filter. So we talked about adding in a freewheeling diode to help the current out. So we solved the current problem by making it nice and smooth with a big inductor and a freewheeling diode. That's cool. Now let's talk about that voltage. The voltage is a half wave. The positive cycle is what we rectify. And it's a flat 0 and another positive half and a flat 0. That's a pretty harmonic rich environment. We don't really like that. We want to get that hump to flat DC as well. Notice that we use inductors to flatten out the current. We know we can use capacitors to flatten out the voltage, and this is exactly what we're going to do. We're going to add a capacitive filter. The output DC voltage is not smooth enough for some of the applications, right? I should probably let's do that. I'll fix it on your notes. Or I mean, it's a small thing, who cares? Okay. What device can we use to keep the output voltage more stable? Well, a capacitor would definitely help keep the output voltage steady by being a tank of energy to keep the voltage high in case the voltage disappears. Or if we have too much voltage, the capacitor will absorb the energy instead of passing it to the rest of the load. Okay. So below is a circuit for a half-wave rectifier where we could put this capacitor right here. And this capacitor will help control the positive DC voltage and the negative DC voltage. So your output voltage will be more stable with this capacitor in parallel. Okay. Notice how I also drew this dotted line to show you about to the left of the diode is our AC side, to the right of the diode is our DC side. Capacitor is always going to DC circuit to help smooth out that output voltage. What does a resistor represent in the circuit here? This is just your DC load. Okay, this is a light bulb. This is the pretty much any toaster, whatever you want. Okay. Why is the capacitor installed in parallel instead of series? It's always the big question when you put a filter on, right? Does the capacitors go in parallel, side by side, or in series in one loop? Capacitors and resistors must share the same terminal if the resistor wants to see stable voltage as capacitor. General rule of thumb is when you're trying to control voltage, you need to put things in parallel to share the same voltage. When you try and control current, you need to make sure they're in series so they share the same amount of current. Putting this capacitor in series with the resistor isn't going to do anything because the resistor voltage will change drastically because the capacitor is there as well. Okay, but when we link them together like this, capacitor helps stabilize the current voltage so the resistor gets nice steady output. And that's exactly what we want at the end of the day. Okay. So let's kind of try to quantify what's going on. So here's a circuit with a capacitive filter. Below here is a graph where we can see the input and output voltages and waveforms for the half-wave rectifier. Notice the black line. This is our AC waveform. For 180 degrees, we're positive. Another 180 degrees, we're negative. Then positive, negative. This is just AC input. Now we know with a standard half-wave rectifier, everything negative gets chopped off. So we will get a positive voltage. And normally we'd go back down to zero whenever the voltage source is going away. But because the capacitor is here, it's going to help us keep that voltage steady. So the voltage peaks out right here, where this voltage source, the AC voltage source, is controlling the voltage out here on the DC side. But once the AC source starts losing its voltage, the capacitor will then take over and say, hey, this blue line, I'm the capacitor. I'm going to keep the voltage as steady as I can. Now, the voltage does go down because every second or every millisecond that the source voltage isn't the highest, the capacitor is dumping energy into the circuit. So right here, at this peak, the capacitor is full of energy. It's very stiff, has a very high voltage. But every millisecond that goes by, we're dumping energy out. We're going to lose voltage, right? So eventually, this top part of the capacitor might be 100% full with that very high voltage. But as time goes on, it's going to go to 80% to 60%. It might go all the way down to 50%. So we get less voltage than we were 100% because we don't have that much charge in the capacitor. But this is still better than zero, of course, right? And so the capacitor will bridge over the voltage to keep it positive until the next AC waveform comes about right here. So the AC waveform returns from the source, and then we supply the output voltage. We pick it back up to its maximum, and then the capacitor comes in and takes over. And we pick up the AC waveform, will then pick it back up to maximum. And now your output voltage is kind of this high point, middle point, high point, middle point, which is much better than going from high to zero, okay? And that's a huge help on the output. A capacitive filter on any rectifier is almost mandatory if you truly want a near DC output voltage output, okay? How does a capacitor affect the output voltage? Helps keep the voltage closer to the peak value. So right here is a peak, right? And makes the output more DC-like. This combined blue and green line together is way more DC-like than anything going down the zero axis, okay? And the difference between the lowest point that the capacitor shuts off and the AC waveform returns, and the highest point where the AC waveform goes away, that's your delta V out. This is your ripple, right? This is kind of like I'm going from 90 volts to 120. So my difference is 30. They're just throwing some numbers out there. Okay. So at the end of the day, much better output waveform with a capacitor involved. It's a pretty good idea to have one. So let's do some circuit analysis real quick to see what happens whenever things are changing. Right? So let's look at the half-wave rectifier when the AC source is conducting. So this voltage source is on this positive cycle. So we turn on the circuit, so everything gets charged up to about right here. So this green line, current flowing out the source, going through the diode, it charges the capacitor and the resistor. So that's the big thing, is when the capacitor isn't holding up the voltage, it's taking in the voltage, or taking in the current rather. It's absorbing energy. So right here in this green line, capacitor is absorbing energy. Then right here, it releases it, but then the AC waveform comes back and it absorbs it as well. So this source does a double duty of not only sending energy to the resistor, it also has to send energy to the capacitor, so it can then, the capacitor can work whenever there's no source connected. Okay, and notice we'll always have this little small charging cycle right here. Charge up and send power to the load. Then do nothing. Charge up, send energy to the load, do nothing. That's what the source is going to do now. Okay. So when's the diode forward bias? What happens in the circuit? Number one, sends power to the load. Number two, charges up the capacitor. Once the capacitor is nice and charged, we can then go to the other half where now the capacitor is the source. So now the voltage, the AC voltage kind of dips down a little bit. We're on a declining waveform here. The capacitor says, okay, I want to keep this top voltage as high as possible. The AC source is going dipping low. So this blue part right here will have a higher voltage than the AC source. So this diode will become reverse biased. So the AC source doesn't conduct anymore. It's gone. All that's left that's moving in the circuit is the capacitor is now pushing current out of its terminal to the resistor to keep this voltage out, V out steady, and then returns back into the negative terminal capacitor. So right here, current's going to keep flowing through the resistor, and V out is positive. One big thing to note is whenever the capacitor is discharging, notice the current is going the opposite direction of the IC arrow. Okay, whenever the voltage is high, current enters into the capacitor, right up here. See how we drew the arrow goes into the capacitor like this? But whenever the capacitor is the one discharging, current needs to flow out of the capacitor, right? Charging, current comes in. Supplying, current goes out. Okay, just want to point that out. So right here in blue, this is whenever the capacitor is supplying the voltage, it's discharging its energy to the resistor. Okay, so when is the diode reverse bias and what happens in the circuit? Capacitor keeps the output voltage steady right here, and it keeps supplying the power to the load. So that's another big advantage from the resistor standpoint. It doesn't turn off. Before, you had the AC voltage and then nothing happened, and the AC voltage, nothing happened. From a light bulb's point of view, it's like turning on the circuit and turning off the circuit, on, off, on, off. That can damage some equipment. It's not really that good. It's much better to have this kind of more steady output voltage, so your load is constantly being fed energy, is not getting disconnected, right? So that's a big benefit of a capacitive filter. Now, what's a trade-off? You got to remember, every time we play with capacitors, they can be pretty dangerous. They got some pretty big trade-offs. We got to make sure we design correctly. Okay. So far, this sounds like a great deal. So why wouldn't we just put a capacitor everywhere? What's the trade-off for this quote free voltage? Because we are pretty much getting free voltage, right? So for the capacitor to operate, it needs a lot of current, like a lot of current. So very high current, high source current is needed to charge a capacitor. That's the big trade-off. Okay, so if I want constant voltage, I need to put huge amounts of, if I want constant voltage in output, I need to dump a lot of current into the capacitor when it's charging. Okay, So when the AC source is on and conducting, you might have five times more current going to the capacitor than it would have gone just to the resistor alone. Okay, and we have to design for that. If I initially thought I'm going to have 10 amps, but I'm really having 50 amps, some things in the circuit are going to have to change for that. Okay. Now, when do we remember? When do we charge the energy in the capacitor? When the diode is forward biased. We just said that current it flows through the diode, charges the capacitor, and powers the load. Okay. The source voltage is going to be greater than the output voltage. That's why the diode conducts. And how much current is needed? Well, that's always IC is equal to C times dV dt. So depending on change in the voltage across the capacitor and how big the capacitor is, that's how much current is going to flow. Right when you turn on, you're going to have a huge spike in current. But the longer you stay on, the current's going to get less and less and less. That's that decaying time constant of current flowing into the capacitor. Okay. What do we need to do to accommodate this giant influx in current? You need to upsize the current ratings for your equipment. So this diode will always let current through, but when you realistically buy a diode from a store, there's going to be a threshold operating current. If I expect 5 amps normally, but a spike of 50 amps, I cannot get a 5 amp inductor and expect it to operate. When it shoves 50 amps through, you might overheat it and burn it. So there's always going to be a I max or I amplitude or a maximum current a diode can take. You need to make sure that can handle your current spikes. In this case, we need to size it for 50 amps, not 5 amps. Okay. And that's a very amateur mistake people make and end up burning equipment and wondering why. When there's a capacitor nearby, current spikes will happen. And you just need to make sure all your equipment is sized for that. Okay. So how do we quantify that mathematically? What's going on? So the output voltage has two distinct phases, right? When the AC source is on and the diode's conducting, the output voltage is just the AC waveform coming in. There's a cutoff point where the AC voltage starts dipping down, and then the diode turns off and the capacitor turns on. And at that point is this V theta. This is kind of right here, right after, it's like right after the peak, almost the peak, maybe slightly, a few degrees afterwards. This is where the capacitor takes over and then the AC source shuts off, right? And then you have this, whatever this output voltage is right here, this actual number, it then has a decaying time constant. That's what V out is. And how do you do decaying time constant? It's always e to negative omega t. And this time we got to put a minus theta because we're starting a little bit later at this theta right here. Okay, this could be like 100 degrees or something. So, but it's always e to negative omega t divided by omega RC. That's that standard decaying time constant you've seen in any time you do a capacitor. Okay. How do you figure this theta? This theta is just a tangent inverse of negative omega RC. And this could just be hard calculated, right? You're going to know your frequency, your circuit. You're going to know your resistor. You're going to know your capacitor. Again, it'll be like 100 degrees or something like that. Okay. Now, if we choose a really big capacitor, meaning 10 times capacitor is 10 times bigger than a resistor, we can make some assumptions. We can assume a big capacitor is going to turn on not at this theta, but pretty much exactly at the maximum. So this theta is roughly equal to 90 degrees, or this exact tip right here. This is good because it simplifies calculations. I don't want to have to sit there, is this theta like 100 degrees, 102 degrees, whatever. If I just assume a big capacitor, I'm just going to say this is 90 degrees right here. Okay. And the absolute maximum, where this value right here is the actual maximum, not off a little bit. Okay. And so remember, the whole point of this is to get a more DC-like output. So the bigger capacitor, you see this waveform as it goes down, a bigger capacitor actually makes it more flat. So this is maybe 10 times bigger than my resistor. My output waveform will actually be almost flat. You see how it goes, barely goes down, charges a little bit, barely goes down, charges a little bit. This is a better capacitor filter than the previous one where it dips down a little bit. Okay. And the reason why the voltage is so stiff is because at this point, the capacitor is 100% charged and we dump energy out to about this point, but we could went from 100% charge to 90% charge. We only use 10% of the capacitor's energy tank, and then we are back up with the AC source here to refill. So in essence, instead of going from 100% to 50% and back to 100%, we went from 100 to 90, 100 to 90. And that way, most of the energy is not used, it's sitting there. That's how we get that very stiff high voltage. The more energy capacitor, the stiffer the voltage is. Okay. The trade-off to this is you're not using 9% of your capacitor. It's kind of being wasted in one sense. And that's bad because it costs more. Obviously, a bigger capacitor costs more than a smaller capacitor. So you'd have to weigh, is it worth having this very stiff DC output versus a capacitor that could be 5 times more expensive than a smaller one with a wider ripple. And that's a design choice, right? It's always dollars versus performance at this point. And you'll have to talk with your vendor, your specifications, that your equipment you're making, and you'll have to make that call. Okay, that's for the voltage. Now we need to turn around and look at the current a little bit more. So remember, there's a trade-off for using a capacitive filter, and it's the high current. We need to calculate this high current to then figure out how big of a diode do we need. So what are the two components of the diode current, ID? Well, just using basic node analysis, ID splits off into IC capacitive current and ID IR resistive current. So ID must equal to IC plus IR. Okay. Capacitive current, you can figure this out as omega C Vm cosine of theta after you do your derivative. And then for the resistor, it's just pretty much Ohm's law, Vm sine alpha divided by R, and that's equal to Vm, and this is just arithmetic, you just take the Vm out, and then you have this, okay? Where, omega, that's fixed in the circuit, C, Vm, R, what's this alpha? Alpha is basically whenever this capacitive voltage meets the AC voltage and switches over, and where the AC voltage starts supplying the circuit. This is also when the current starts flowing back into the capacitor. So we need to kind of figure out what this alpha is going to be, and that's just based on the size in the capacitor, which we'll talk about in the next page. Okay, so everything here should be known. This should just be a hard number crunch, and then you'll get your maximum peak current and what design specifications are needed to consider this peak diode current. Well, you need the maximum peak current limit of the diode itself. So when you go buy this at a store or online, there's literally going to be like maximum current, peak current, right, that this diode can handle. And if you don't have this maximum peak current and you have a lower, smaller diode, when you initially start charging capacitor, that huge inrush of current, you might end up burning up the diode and then your circuit doesn't work anymore. Okay, so you absolutely have to pay attention to the peak current and just size your diode accordingly. Okay. Now, let's start talking about how to calculate the capacitance, because that's the other big factor in the circuit. Right? The size of your capacitor is always going to be based on your output ripple. If you want a very tight, thin, or very small output ripple and a very flat, even DC output, you're going to have a huge capacitance. Your C value is going to be big. If you're okay with a pretty big output ripple, you could get away with a smaller capacitor. Okay. So the quantity here that I really need to look at is your maximum value, Vmax, which is the absolute peak of your AC voltage. So right here, this could be like 100 volts, the absolute peak. Okay. Where your capacitor ends up, where your capacitor will start discharging its energy, keeping the voltage steady for a certain amount of time before the AC waveform picks it back up. Where this happens is your minimum voltage. Minimum voltage was when the capacitor is at its lowest point, and then the AC voltage turns back on, and now we're climbing back up. And this is your minimum voltage, V min. And this up and down motion, this is just your capacitor charging and discharging, right? The difference between V max and V min is your delta V out. So if my maximum voltage is, let's say, 100 volts, my minimum voltage is 80 volts, then this delta V out is 20 volts overall, okay? And this is a design choice that you need to talk to the vendor or the customer rather, or whoever you're making this for. We all need to agree what is this upper and lower threshold. Okay. If I can only, let's say this is 100 volts, I can only go down to 90 volts. That's a 10 volt difference. That's about 10%. Okay. So my delta V out will be 10. I need to design to make that happen. Okay. If I have a very sensitive electronic where I can't get more than 5 volts lower than 100, I can only go between 100 and 95. My delta V out is going to be 5 volts, and we'll have to figure out the capacitor to make that happen. Okay. How do you actually quantify these two numbers? Well, at the end of the day, your output voltage is DC waveform, or we want it to be a DC waveform, and we need it to be a smooth out voltage wave signal. How can we define the ripple in the graph above? I kind of already talked about it, but let's put it into hard equations. Delta V out is always equal to the V max minus the V min. That's the difference here, where V max is literally the highest output voltage of the AC source, VM, subtracted by VM sine of alpha. Okay. And again, this alpha is, you can play with it to calculate this minimum voltage, right? And this is where the vendor comes in. So if I'm your customer and I say I want Vmin to be 95 volts, you could say VM sine of alpha, this has to be 95 volts. You now know alpha. That's just a number crunch in the calculator. And this alpha is very important because you can go back over here and figure out what your diode peak is going to be. Okay. So this output ripple does two things. It sets the maximum peak voltage for your diode, and it's going to help us figure out the capacitor here as well. Okay, so we now have this delta V out. We could then take it over here and we can calculate capacitance. So how can we quantify that in our design? And have a rectifier with the C filter. So at the end of the day, V out is that 5 volt, whatever the customer says. It's roughly equal to, and it's close enough, to VM 2 pi divided by omega RC. 2 pi divided by omega can be converted to frequency down here, and at the end of the day is the output ripple delta V out is equal to VM over F times R times C. VM is constant, that's from the AC source. Frequency is fixed to 60 hertz or whatever your source is. Resistor, that's just the resistance of the load. The capacitance that's the number you choose. So everything here, these three are known. This delta V out, this is given to you. This is a arithmetic in your calculator. You get a capacitor. It could be like 1 millihenry, 50 microhenry, 1 millifarad, 50 microfarads, or whatever that number is going to be. Okay. So big thing here is the output ripple. It pretty much drives the whole entire design. Whatever this is will tell your alpha to do your diode design and also tell your capacity, how big your capacitor is going to be. Everything else is already done for you. Okay. So in summary, you have rectifier circuits with filters. Number one, why do we install a freewheeling diode in a rectifier circuit? This is kind of a little additional feature we put in the halfway rectifier. Remember, it's an alternative path for the inductor current to travel when the source is on its negative cycle. That way we're not having negative voltage and messing the whole output up. Okay, very good idea to have this. What is the benefit of having an inductance present in the rectifier circuit? So this RL, this inductor, it has some bad things, but it has some good things as well. One of the biggest things it does, it helps smooth out the current to lower the harmonic current value. Okay, so an inductor is very good in creating that nice flat DC output current. What can we also do to lower the output voltage ripple to make the output voltage more constant as well? Add a capacitor in parallel to the load. This capacitor helps fight any changes in voltages and smooth out the output voltage. Okay, so at the end of the day, freewheeling diode is there to help bleed out some of the inductor current. Inductor is also there to smooth out the output current. You also should put a capacitor to smooth out the output voltage. Right? In reality, you put them all together, and that's a good package deal. A lot of rectifiers are built like this. Okay. So that's all I have for today. We're going to come back next week. We're going to talk about what we call full wave rectifier, which is a better version of everything we talked about here. And that's pretty much what industry we use in today's world, right? Half wave rectifiers is kind of a cheap alternative. So we're going to redo everything and use all these same techniques with a full wave rectification, and then we'll see where we go from there. Okay. So just want to say thanks for showing up and listening to me, and hope you learned a lot this week about the basics of rectification, certain rectifiers and rectification. We're going to come back next week and just build up on it and get to a more advanced system. Okay. So hope you guys and gals have a good day. See you later.